Good afternoon. We are the Rose-Hulman team for the Solar District Cup Challenge. Before we begin, I would just like to thank a few people. I would like to thank our faculty advisor, Dr. Walter, for being there during the year for us, as well as our clients, our senior design clients, Chris Ware and Ben Huckba, who put us onto the idea of the Solar District Cup Challenge and were also there supporting us throughout the entire year. My name is Lee Thrush.
Sorry, I'm not sure what happened, why it got out of presentation. I'm Patty Geraldo.
I'm Nathan Pryor.
And I'm Justin Ogasawara.
So getting into our team structure a little bit, we did this competition as our senior design project. So each of us took at least one of the different items to kind of be the leader of. Lee and Nathan only took control of one of the different areas because those areas were a little more heavy work, where Justin and I took control of two different areas. And if anyone needed any help, if it was a one-person group, we helped them if they needed, but we kind of tried to distribute the work pretty evenly. Really slow. So with so many advancements in the solar energy generation and battery storage, there's been a big decrease in cost and an increase in industry use in the past 10 years. And while the solar industry has been developing rapidly in the last 10 years, there are still lots of opportunities to take the solar generation to a larger scale. And that's why the idea to incorporate solar generation and battery storage together can help us branch out to larger districts like the University of Central Florida. So this is why our team wanted to take on this challenge to design a solar plus storage system for the University of Central Florida that will help offset, and there's a typo here, it's supposed to be 13 buildings on campus while paying back our initial investment within 20 years. And we believe this will help UCF be one step closer to their goal of carbon neutrality by 2050. So some things that we considered before we kind of started planning was we wanted to ensure that our PV system would comply with UCF's plan for their campus. So with UCF having the goal to reach the carbon neutrality by 2050, they have a PV prioritization plan to help the campus have a more smooth development of and installation of any proposed PV system in selected areas. UCF's zoning is also a multifamily dwelling district. So there might have been some certain coding constraints to consider when developing a PV system, like having to put a fence around ground mount or only being able to place in certain areas. So that was definitely a consideration. And also iridescent values of the area kind of influence how much energy we can produce with solar panels. But seeing as Florida is a sunshine state, we weren't super worried about any of that.
Okay, so here we are.
So the University of Central Florida provided the team with data from 15 different buildings. The team's plan was to generate enough energy to power as many of these 15 buildings without having excess power larger than what we are allowed to produce and sell back. The team was able to provide enough energy of roughly 11.67 gigawatt hours to power 13 of the 15 buildings, which consumes roughly 11.54 gigawatt hours. The team is using two different areas to utilize for PV and battery systems. The slide shows area 1 outlined in red, which is the area on campus we placed rooftop solar on. In this figure, you can see all 14 of the buildings we placed solar panels on and the total power output of this area, which is 6.8 gigawatt hours. So outlined red on this slide is area 2, which is the space off campus we were allowed to place ground mounted PV and battery systems on. The team only added enough solar panels until we produced enough energy, which is roughly 4.9 gigawatt hours, to not exceed the excess power we were allowed to produce. And we also placed all our batteries on area 2. And so from both areas 1 and 2, we were able to produce a total of 11.67 gigawatt hours of energy to offset the power for the 13 buildings on campus.
So solar panels and inverters are the most important components we needed to generate the solar energy. So we chose a solar panel on the left because of its super high efficiency, which is around 21.7%, and the high output power of 470 watts, and it has a pretty low cost per watt. And the inverter we chose is there on the right. The main reason we chose that one is because it has a large number of solar panels it can handle, which is around 140, since it does have 10 PV string inputs. So the team used a total of around 19,804 panels, with 12,104 being in area 1, 7,700 in area 2. And we used, I don't know why that moved. I don't know if I have control anymore. Okay, there we go. Sorry about that. And we used around 119 inverters in area 1 and 70 in area 2 for a total of 189 inverters.
On to the mounting system. So in area 1, our team utilized 2 different mounting schemes. The first being a rooftop ballasted system, which is a cheap and easy to install mount. And it's held on by weight and does not penetrate the roof. The second mounting system we chose is a solar carport for the parking garage. This is so that UCF personnel will still be able to park on the top layer of the garage. In area 2, we see that we utilized a simple ground mount system. For both areas, the team decided on a tilt angle of 0 degrees to allow the most energy production due to the panel-to-panel shading that was present if there was a tilt angle. The azimuth angle, or the angle the panels are rotated with respect to the north horizon, varied based on what maximized the number of panels on each building roof.
The amount of energy sold back cannot exceed the daytime minimum load at any 15-minute interval. This amount was found to be around 2,326 kilowatts by running a base case power flow model. So in order for our distribution system to stay within this limit, the team calculated the amount of battery storage we would need to be around 3,074.24 kilowatt hours. So in order to have this much storage, we need 416 of our 7.4 kilowatt hour batteries. And that's 32 parallel strings of 13 batteries. The 13 batteries in series are to ensure the proper voltage is reached, and the parallel strings is to ensure the storage capacity is reached. There needs to be a charger per string of batteries, so we have 32 chargers, and our controller can handle up to 20 strings of batteries, so we only require 2 different controllers.
This figure lays out how our system will connect to the campus via their transformers. You can see the college and the inverters and panels on that building, and then which transformer they connect to. This is a lower level diagram showing how the health service building specifically would be laid out, and how the controller would be connected. You can see we have the panels connected in series and strings that go into switches to the controller, and an additional 2 switches from the controller, 1 to the batteries and 1 to the inverters. The inverters then connect to the low voltage side of the transformers throughout campus. The switches are activated by the controller to control how power flows throughout different times of the day.
Here we see the 1-year construction plan that our team devised. We all did extensive research to find the appropriate permits and codes needed for this type and size of project. The team also priced out the cost of subcontractors in excavating area 2 to ensure all aspects of the project's costs were included. So in this slide, you would see that timeline and how it is divided up.
The goal of the distribution analysis was to show that our system can connect to the existing grid on campus without leading to any violations or harming the grid. This shows that our system remains within the voltage limitations. As seen in the figure, the red lines represent the maximum and minimum per unit voltages that the lines throughout campus can have, and the blue lines represent the actual voltage. As you can see, our voltages remain within those maximum minimums, and thus we don't have any voltage violations. The team also had to upgrade transformers throughout campus in order to, because we were running into overload issues on transformers throughout campus. We added 2 1.5 megavolt amp transformers for area 2, and we upgraded 4 transformers to 750 kVA and 3 to 500 kVA in area 1. The transformers can be seen in the figure, and they're marked out with the triangles. And those are the transformers we connected to. Ultimately, we chose to upgrade transformers over downsizing our system or introducing more batteries, because we found that it was the most optimal solution for what we wanted to do. We did not want to change our energy offset to have a lower or to decrease our energy offset. And if we wanted to keep the same energy offset and have batteries, we found it would be much too expensive to implement. In addition, it would increase our hosting capacity. So after the lifetime of our system, if we wanted to upgrade our system, we could do that and likely not have to upgrade transformers again. In order to maximize the energy offset produced and used through our batteries, we wanted a set of controls that could trigger to charge to curtail overproduction, and that would trigger to discharge in a controlled manner. We found that using peak shaving for the charging control best curtailed the overproduction while maximizing the energy offset from the solar production. We then used a time of day based control for the discharge to maximize the amount of hours we can produce power for the batteries. The two figures show a year long of power through the batteries, and then the one on the right is a more zoomed in picture. As seen in this slide, our system only sells back 1,876.01 kilowatts over the course of the year, which is below the daytime minimum that we've had found. Thus, our system does not violate the contract with Duke Energy.
So getting to the financials, our system is sized to be 11.7 gigawatt hours, and the total price came to be just over $30.8 million, which does seem high, but it does include the total price of excavation, mounting, tree clearing, fencing, gravel placement, labor, and so on. Although it does seem to be high, the overall project internal rate of return, or IRR, is 3.87%, which we see on the picture in the left. This number directly correlates to the time it will take for the system to pay itself off, so a higher value here means a faster payback time. On the right, we see the net present value of our system over 20 years in today's dollar amount. So here we see the campus is saving just a little over $20 million when choosing to go with the solar system. So with the IRR of 3.87% combined with our total price of around $31 million, we see that the system will pay itself off in around 14 and a half years, which is shown in this figure below.
So just to summarize, our team is proposing a 11.67 gigawatt hours of solar generation with 3,074.24 kilowatt hours of storage for the University of Central Florida that will help offset the energy consumption for 13 buildings on campus while paying back our initial investment in about 14 and a half years. And that is all we had for you guys.